Hey everybody, I want to do a quick demonstration of the Lotka-Volterra model for interspecific competition. So we're comparing the two different species that are competing against one another, and this is somewhat similar to the previous Lotka-Volterra model for species interactions, predator-prey interactions. I guess we're about halfway through the semester now. We had our summer break last week. I was on family vacation then, so sorry if you tried to contact me and I was a little late getting back to you. We went to the beach and I got stung by a stingray, so that was loads of fun. And I guess there's some irony in that, and that have a background in fish ecology. But anyway, we're back and getting back going with our responsibilities here at Clemson. So this model is similar to the last model, as I was saying, and I want to show you briefly how the model works. And there are two tabs you'll notice. There's this Lotka-Volterra tab for interspecific competition, and then there's one for zero growth in isoclines. So I'll talk about that as well. But the parameters that I want to go over and talk about are R sub A, R sub B, so those are the rate of increase, intrinsic rate of increase, and then Ka and Kb, those are the carrying capacities. Na and Nb, those are the original populations, and then alpha and beta in this model represent the competition coefficients. So how much of an advantage one species has in competition over the other, what effect that one species has on the population of the other species. And so just quickly, I want to change a couple of these. So we're going to change first the rate, and so you can see if I change from 1.2 to 1.4 and hit enter, you can see that our competition sort of decreased, the rate for or the competition, the population number for species A sort of changed, and it increased up to getting closer to population of species B. And so if we can do that again, we'll change it by 2 again, 1.6. You can see it gets closer again. So I'm going to put that back to 1.2. And then carrying capacity, so if we change our carrying capacity from 400 to, let's say, 300, you can see that we end up with this really strange looking graph where the population of species B reaches its carrying capacity, while after some period of time, the species A decreases eventually to 0. And at that point of 0 competition is when species B can actually acquire its carrying capacity. It can't reach its carrying capacity otherwise because it's in competition for some resource with the other species. So we'll put this back to 400, and then we can change the initial populations. We start at 10 for each, or 10 and 20. So if we change 10 to 20, and you'll see that the two populations at that point become equal. We change that back, and then what if let's change this to 20 and then change the other species to 10, and you can see that the two species sort of flip places in terms of their population numbers. And then lastly is the competition coefficient, and let's change the alpha to 0.7. And you can see that we get a similar effect as when we were changing the carrying capacity earlier. You also notice that alpha and beta are inverses of one another. Okay, so alpha of 0.5 is the inverse of 2, or 1 over 2. So that's the competition model. Now I'm going to look at the zero growth isoclines. And in this example, the only two parameters you need are the carrying capacities for both species and the competition coefficients. And what we're really interested in here is the point at which these two lines cross, and that gives us the point at which the population of each species at which they can coexist indefinitely, barring any other changes. So if we just look at some changes here, so start with the carrying capacity of 500 for species A, and we can change that to 600. And you can, not 60, 600. And you can see how the curve at the bottom changed. If I make them equal, you can see what happens. Go back to 500, and then let's say we change the double. So you can see that there is these two species could not coexist in this situation. So let's put it back at 700. And then alpha, if we change alpha from 0.5 to 0.7, you can see that that really changed where the species could coexist. So in this example, there'd be a really high population for species B and a really low population for species A because of the increase in competition between the two, and species A would sort of be the loser in that situation. All right, so that's that. Just want to do this quickly. There's going to be a follow-up quiz related to this, so be sure that you follow the directions, reach out if you have any questions, and I look forward to seeing you guys again here soon.